Good morning, everyone. As we discussed previously about supercapacitors and the basics of the supercapacitors and how supercapacitors measurement has been done, and secondly, on the next day, we are discussing how the materials used and what is the experimental procedure and in what process we are synthesis materials, and in what parameters we should take consider for the supercapacitor devices. And today we will discuss about the device architecture and the device fabrication, and also we are discussing about the supercapacitor performances and how its application. So okay, for till now we are discussing about the synthesis process. So now we have some material, but the next step and the most important thing is how to make the device. So there are so many processes to make the device. Most common and the most many people are using to make the device was first the slurry preparation. During this slurry preparation, they deposit their material on the current collector. So to get the slurry preparation, we generally want to consider the four components. The four components are: one is active material, that means the materials which we synthesize, and next one is the carbon black, and which I will go solvent to make the good slurry. So first of all, active material. Active material we are using because our main purpose is that the superior material that can used in a supercapacitor application. So that is the active material. And carbon black. Carbon black generally used for supercapacitor device fabrication because it will improve the conductivity. And third one is the binder. We used binder so that it can it has generally binder has a adhesive nature, so it can stick our material into the current collector so that any leakage current drops. And then solvent we use because all this active material, carbon or the binder, that is all are in the powder form. But in case of deposition, we need a good slurry or solution where we can use this powder and make a slurry, or you guys can say it is a ink type. So how to make the slurry preparation? So first, the most common solvent we are using is the NMP. NMP means N-methyl pyrrolidine. So this is the organic solvent, and goodness of this solvent is it is dry easily, and it cannot harm anything of our active material. So generally, the first we use our binder, and the ratio for the metal, if we want to deposit the metal oxide, the ratio of active material and carbon black and the PVDF is 75 is to 15 is to 10. That means if we want to make suppose 100 mg of slurry, then we have to use active material about 75 mg, and 15 mg is the carbon black, and then 10 mg is the binder. For in case of any carbon material, we also there use the carbon black, and the ratio is the 85 is to 5 is to 10. We generally we fixed the binder, because if we vary the binder, sometimes because binder is a polymer material, so it may reduce the electronic properties of our active material, or the deposition or the slurry is not properly done. So what we will do first we measure the amount of binder. Suppose we used PVDF. PVDF is the polyvinyl difluoride, polyvinyl fluoride, sorry. And suppose we measure a required amount of, for example, 10 mg PVDF, and mix it well in NMP, so that first all the PVDF are dissolved. After this dissolve, we will clearly see in the NMP it becomes a glue-like structure. And after that, we mixed active material and the carbon black at the same time, and stir this slurry for a couple of hours. So once we find a good type of ink has been made, then we can say the slurry is well prepared, and after that we coat this slurry into the current collector, and after coating we will dry it, and then we have our electrode material, so that can be directly used in supercapacitor application. Whether it is in we can use it is in 3 electrode cell system, that means the individual electrode performance, or we can assemble it to make the device. Second one is the electrophoretic deposition. As we discussed it last class, where we can use electrophoretic deposition, not only the deposition or making the thin film, but we also electrophoretic deposition used for synthesis the material. So I will repeat it again in what we will do in electrophoretic deposition. For example, we want to deposit our metal oxide or the MnO2. So suppose we here we use also NMP as a solution. So what we will do, we wet some amount of the NMP and some amount of the metal oxide, suppose MnO2, and mix it in NMP and make a good solution. And after that, we need to charge our suspension. So we will add a small amount of hydrochloric acid. So the small amount of hydrochloric, this will charge the MnO2 particle, so that electrophoretic deposition may happen. After that, we used a power supply where we use PT platinum as a counter electrode, and we used our substrate, whether it is a nickel foam or nickel foil or any stainless steel or any other substrate that we can use it. Remember one thing, when we use the APD or else in slurry, anything, before coating our material, it is required to clean the substrate to reduce its residuals. Okay, so after clean the substrate, we dip into the solution and apply a power source. Constant, suppose we apply a constant voltage. Once we apply a constant voltage, we can find inside inside this chamber, inside the setup. Suppose in case of MnO2 is deposited onto the substrate, and we will for our requirement, we will fix time. For example, suppose 30 seconds, or for example, suppose 45 seconds or 1 minute. After 1 minute, we stop our experiment, take out the substrate and clean with DI water. So that outer the undeposited MnO2 onto the substrate can remove, and or any residuals can remove. Finally, this electrode we will do this in vacuum dry. So once for overnight, once the vacuum dry has been done, then we can use this electrode for supercapacitor for measurement. Third one is the direct growth. Till now, as we can, I will say, I say that in slurry we used a binder. So if amount of binder is higher, more binder, it may reduce the conductivity, that can degrade the electrochemical performance. So one method is the direct growth method. So generally in hydrothermal synthesis, we use the direct growth onto the substrate. So in direct growth, what we will do is we first clean, as I said, first we clean our substrate. And then during the synthesis process, suppose in case of if we want to deposit as I say here, suppose in case of nickel cobalt oxide. So what we will do for nickel cobalt oxide, separately we make the precursor that contains the nickel precursor and cobalt precursor. So once the precursor is has been done, we will put it in hydrothermal Teflon reaction vessel, and when it is properly filled, or whatever amount we are using, after that we place our nickel foam onto the Teflon reactor. And one thing makes sure that when we deposit our substrate, we will cover some part of the substrate, because this is the direct growth of material, and inside this chamber we don't know what will happen if we don't cover it. So it might be possible all the material deposited through all the substrate, and then we don't have any other option as a current collector. And if these things happen, that is not good. To prevent this, we first cover some part of the nickel foam and dip it in the Teflon reaction and do the hydrothermal process. After hydrothermal process, we just take out our nickel foam, suppose in case nickel foam substrate, and wash it and dry it. Okay, and second thing, one more thing is, generally if we want to make any metal oxide by the hydrothermal, generally in the hydrothermal reaction, it is growth as a metal hydroxide. It is not being a suppose in case of the nickel cobalt oxide, it deposition, it happen in the nickel cobalt hydroxide. So from hydroxide to oxide formation, we will generally we will do the annealing. So in any gas, whether it is in argon or nitrogen or any other environment, or oxygen, any other environment, we will do the annealing. So once this annealing happen, after finish, we will get the metal oxide that is directly deposited onto the substrate, and we can use it for supercapacitor application. So one good things for the direct growth is there is since there we don't use any binder, so that means the contact between our electrode and the current collector are very good. So overall performance will improve. But there are also some problem that that is suppose in case of the nickel foam, and we use the electrode and do the hydrothermal. Inside the thermal, some part of the nickel foam also react with react with our precursor. So during the measurement, if we want to calculate the specific capacitance, volumetric capacitance, or mass specific capacitance, that means the unit must be in farad per gram, then we need to take care this method. Or else otherwise, to prevent this, some people are using any carbon cloth substrate. For this, there is this can reduce this mass loss or this reaction onto the precursors and the substrate. So for example, one more example is they directly grow the cobalt oxide nanoseed onto the and the carbon nanotubes onto the substrate. And how they do during this direct growth or hydrothermal, they first use the cobalt oxide and the substrate, and after and perform the hydrothermal reaction, and after that they can get the cobalt oxide and the carbon nanotube composite onto the substrate, and they directly use it as an electrode material, and they get a redox peaks or good electrochemical performance, good specific capacitance. The devices is achieved around 100 farad per gram. Also, these devices achieve very good energy density and the power density. Another deposition techniques is the vacuum filtration. So suppose if we want to make a flexible devices, some people are using, we can use the vacuum filtration. So generally this is the vacuum filtration setup. Here what we can say it, this thing is called the funnel or the Buchner funnel, and here generally we used a rubber sleeve so that it can be well tightened to the flask. And this flask, this is the round bottom flask, and one point is the empty, and we can connect here a vacuum instrument or vacuum machine. So what we will do, and here we use a filter paper. So suppose if we want to make, suppose graphene paper. Okay, suppose if we want to make the graphene paper, so what we will do, first we put it here a filter paper, and separately we used a very thick, or you can say it as the desire of your paper. We can make the slurry or thin film solution of the graphene. And what we will do, we put it over here, and we turn on the vacuum pump. So during the vacuum creation, the liquid is fall down, collected over here and onto the filter paper. The graphene thin film is deposited. So once the all performance has been done, so after that we take it out, this filter paper, and dry it, and after that peel off the filter paper, and then we can get a very good uniform graphene paper. And also we can use it in supercapacitor applications. for the flexible devices. Till now, we are saying the different some techniques where we can make the device. Although there are some other techniques, as we can say, is screen printing or doctor blade techniques, which is doctor blade and the skin printing is bit complicated. We will skip this technique, but many other, as I can say, is many other techniques we can make the electrode. So now we have electrode material, and we measure its specific capacitance. But for the device fabrication, we need to optimize. What is the optimization? The main optimization is the charge balance, and the formula is the Q plus equals to Q minus. So that means the positive electrode charge must be equal to the negative electrode charge. And the formula, based on this formula, if we want to calculate the mass specific capacitance, that means how much amount of material we deposited, then we need to calculate the mass balance, and based on the positive electrode and the negative electrode capacitance and the voltage window, we can get how much mass we can use it in positive electrode and also in negative electrode, so that it can optimize or it can show the best performance. And if we want to measure the aerial capacitance, then we need to get the area ratio of positive electrode and the negative electrode. Here one is example. Suppose because our main desire is the high energy density, that means formula is half C V square. So based on this, suppose if we calculate, if we want to make the asymmetric devices, positive electrode and the negative electrode masses. So this is the formula, as we can see it here. Suppose for negative electrode, its voltage window is suppose 0.8 volt, and if the positive electrode, it suppose it is 0.6 volt. So that means if we make a device, it might be achieve around 1.4 of the 1.5 volt voltage window. And how we will use this? Suppose in case of the nickel cobalt oxide, okay, nickel cobalt oxide, and as a negative electrode, suppose in negative negative or graphene or CNT, suppose graphene, it shows the specific capacitance is around 150 farad per gram, and the voltage window is the 0.9. And for the positive electrode, nickel cobalt oxide, and nickel cobalt oxide, its specific capacitance shows 2400, and its voltage window is the 0.6. So we can see it here for the charge balance, since the specific capacitance is huge. One is 150 and the one is 2400. So we need to charge mass balance. So for this mass balance, suppose in we will fix nickel cobalt oxide, we will use suppose 0.0005 gram of nickel cobalt oxide. So if we use 0.005 gram of nickel cobalt oxide in a positive electrode, how much material we deposited onto the negative electrode? That means how much material we deposit graphene. And so based on this calculation, we can say we should deposit 5.3 mg of graphene oxide. So if we deposit 5.3 mg of graphene or graphene oxide and 0.0005 gram of nickel cobalt oxide in both negative and the positive electrodes, then only we can make a asymmetric devices, and that can achieve a voltage window around 1.5 volt, and so the superior performance, as we can see it here. So for the asymmetric devices, it is important to do the charge balance. But for the symmetric devices, because both electrodes are the same material, so it shows the same specific capacitance values. So for the symmetric devices, there is no requirement of the charge balance. So we can just assemble it and make it supercapacitor devices. And next one is, okay, now we already have positive electrode, negative electrode, and one thing is what electrolyte we can use it. So only there are two electrolytes. One is the aqueous electrolyte either, or you can use the polymer gel electrolyte. I am not care about talking about the aqueous electrolyte, whether it is any basic salts like NaCl or Na2SO4 or the ionic liquid or the organic liquid. I am generally says the two types of electrolyte. One is the aqueous electrolyte, that means it is in the solution form. One is the polymer gel electrolyte, that is the gel form. So previously aqueous electrolyte has been used, but the problem for the aqueous electrolytes is its voltage window is the fixed. But for the polymer gel electrolyte, we can increase the voltage window, and as well as it is the safe, because as we know, any devices that might be blast or fire or these things happen, short circuit. Why this short circuit had happened? Because if inside the devices, if all the aqueous electrolytes evaporate, then two electrodes are contact together. So due to this short circuit, these things happen. But in case of the polymer gel electrolyte, it can prevent the evaporation of electrolyte. So as a result, is it safe? And second thing is it can reduce the device's size. Suppose we know long back when we use in mobile, when lithium ion batteries, we see the batteries are too thick, but and that's why the phones also very thicker phone. But nowadays we all see the day by day phones getting thinner. So only thinner phone may possible if their devices or if their batteries are in compact form. So for that case, gel electrolyte are used. So how this gel electrolyte used here? Suppose we see it here in the water solution. We add. Sorry. No. Is there any music? But here there is no music.
Yeah, yes, you continue. It's okay.
Oh, okay. So how to make the gel electrolyte? Suppose PVA. PVA is the polymer material. It's called the polyvinyl alcohol, and it is water soluble. So what?
Yes, you please continue.
Yeah. Okay. Am I audible? Am I audible? Oh, okay. Yeah. So how we will make the gel electrolyte? we used a PVA, that means a polyvinyl alcohol, and it is the water soluble.
Yes,
So
Bhaskar, please continue.
yeah, okay. PVA first, we add PVA into the water and mix it and heat these things. So once it's heated, all the PVA is dissolved in the water, and it becomes the glue-like structure. And then whatever electrolyte we used, for example, or 3 electrolyte, any kind of electrolyte, we suppose in KOH, because KOH it is the palette form or an hydroquinone. So we just add these things into the PVA water gel and stir it. Once this KOH or the HQ is dissolved, and it becomes the clear suspension. So once this clear suspension happen, we just put it in a petri dish and we just dry it. So in case of KOH, it becomes the clear suspension. But in case of if we add 2, so HQ has the different chemical formula, so it is not a clear suspension. But after evaporation of water, like this gel, we put it in petri dish and left it overnight at the room temperature. So at some times these waters are evaporated, and we can get this type of gel polymer film, and we can use this gel polymer film to make the devices, which will be safe, and also it is the compact in size. So now now we have both positive electrode, negative electrode, and the electrolyte. Now it's time to make the devices. So first here I am talking about the symmetrical devices. As I can say, in the symmetrical devices, both positive electrodes are the negative electrodes are the same same material. So and we just assembled it. So here is the one example of the reduced graphene aerogel based symmetrical devices. So how they make this? So they have the graphene oxide suspension, and after performing the hydrothermal reaction, they have the reduced graphene oxide hydrogel, and then after collecting this and freeze drying, they get the reduced graphene oxide hydrogel. And then what because here where I am talking about the in planar devices, I will come what is the planar devices and all. So what they generally do after getting this IRGO aerogel, they press it. So once they press it onto the substrate, it becomes well deposited onto the substrate, and then using the laser source, they make the pattern. So we can clear see it here. They make the pattern where the both electrodes are in plane, and like this. And we can just this is the electrode. We connect it here, one current collector, whether it is the silver paste or gold nanoparticles or anything, we just, or copper tape, we just connect it here. Suppose if we want to check the one device's performance, so we just connect one tape is here and one tape is here, and measure the device's performance. Because, and we put the gel electrolyte, we can see here the small gaps between the two electrodes. We put the electrolyte in between them and we measure, so we can get the device's performance. And to improve the device's performance, because for real-time application one devices is not suitable. So whether if we want to make the series connection, we connect it like this, and if we want to make the parallel connection, we connect it like this. And we can see it here for the symmetrical devices. If we add suppose two devices, if we do the series connection, we can improve the voltage window, because symmetrical devices, its voltage window is the limited. Voltage window is the limited. But in case if we make the devices in the parallel connection, we can get the higher current. So based on what requirement we can connect devices. And since this is the in planar devices, and it is the flexibility, it must be shows the flexibility. So here we can see it here. We can bend our devices, and different bending angle we can check its performance. And we can see here, make sure that many different bending, there is capacitance retention must be the same, not degradation is not suitable for wearable devices. And finally, because finally we make the devices, so it is important that how much time it can sustain, it can run. So we can see it here. For this case, we will do the cycle test. We will run our devices for longer cycle and check the capacitance retention. As we can see it here, for after 2000 cycle, its capacitance retention is almost same. You can see it here, it is almost 100%. Next one, now it is shows the in planar. Now we can say in devices, that is the coaxial supercapacitor devices. So how they do the coaxial? Suppose they use a flexible substrate, that is a normal paper, and that contains the many yarn, and after chemically treatment and the other experimental process, they transform it, and then during the electrochemical EPD method, here they deposit the metal oxides. And also metal oxide, and since this is the paper based substrate and electro deposited, so first we can make the coaxial. Now if we repeat, suppose we first do the metal deposited onto the substrate, because this paper doesn't has any conductivity. So as a current collector, first we deposit a metal, and then we deposit our metal oxide, and after that we deposit our again metal and metal oxide. Like this we can get the coaxial like structure, and and also using the gel electrolyte we can make the supercapacitor devices, and we can achieve a very good specific capacitance. Remember one thing, because this is the coaxial, and all the materials are deposited throughout the year. So that means in that case, generally we are calculating the areal capacitance. That means the how much area material are deposited throughout the area. And also we can check its cycle number, as we can say see it here. after 5,000 cycle, this material can sustain up to 86% of its capacitance retention, and also it shows a higher, very good aerial capacitance around 1,700. And normal capacitor, this capacitance never be achieved. And third one is the symmetrical devices, where they use the carbon cloth, because carbon cloth is such type of substrate that is very good flexibility, and we know all the clothes we are wearing, that is carbon clothes. So that means, for in case if we apply for the application of wearable device, carbon cloth is the suitable substrate, and to make the wearable devices. So here is one example of wearable and the flexible symmetrical supercapacitor, where of Fe2O3 nanoparticle and the graphene. So symmetrical devices. So how they use the carbon cloth, and after cleaning the carbon cloth, the process is called deep coating. So they dip it and dry it. And for dipping, first required a precaution, and dry, and then they do the annealing process. So during this annealing process, the actual chemical reaction happen, and then it becomes the Fe3O4 nanoparticle and the graphene composite. And once they get their electrode, they assemble this in a symmetry or sandwich type. So in between them, they use a separator. Okay, I am saying what is the separator? If we use the aqueous electrolyte, and as I say, if all the electrolyte is evaporated, then evaporates, then it becomes a short circuit. To prevent these things, we use the separator. So generally, separator it can sustain sometimes, and it contains the electrolyte. It has some pores, generally separator, so that that can pass through the electrolytes, through the electrode. So separator are used so that the device safety. So we can see it here. This is the schematic of their devices, where they use the two flexible electrode, and here they use the separator. In case in case of gel electrolyte itself act as a separator, and as well as it contains the electrolyte. So that's why gel electrolyte are used mostly. And we can see it here, how much they make their devices. See, they use the gel electrolyte, so that's why it is good flexible. So if they use the aqueous electrolyte, it can't be flexible, because if then all the electrolytes come out, right? So this is the flexible device applications, and also they achieved very see, if we use the aqueous electrolyte, it may be limited to the potential window up to 1 volt, but they use the gel electrolyte, they can achieve the higher voltage window. And we know that our supercapacitor, the first thing is the energy density, half C V square. V means the voltage window. So if the voltage window is increased, we can see it is the square form. So higher energy density can be achieved. So as we can see it here, they achieved around 1.6 volt, and since this is the flexible substrate, so different bending angle they check, and also they get a good energy density, and also we can see good energy density and the power density. And also we can see it here because of polymer gel and the flexibility and all. And also it depends on the material. You can see after 4,000 cycle their capacity retained up to almost 100%. Next, till now we're talking about the symmetrical. Now the asymmetric. As asymmetrical devices. See, for the symmetrical, both electrodes are same, but for the asymmetrical, different electrodes we are using. So automatically their voltage window is increased, and resulting as a electrochemical performances increases. Okay. So here is the asymmetric devices. For example, they used a cobalt manganese oxide or cobalt manganese precursor related material. In case of cobalt manganese oxide, cobalt manganese sulfide, or cobalt manganese selenide. So three type of material they deposit, prepare by the normal hydrothermal method. So after hydrothermal method, they get the cobalt manganese hydroxide form. So if they annealed in oxygen atmosphere, they might get the cobalt manganese oxide. If they do any and add any sulfur precursors, and then it becomes the cobalt manganese sulfide. If they do the selenide precursor and do the second time hydrothermal, they can get the manganese cobalt manganese selenide related material. So okay, they get the based on that they get the different material. Now suppose they want to make the cobalt manganese selenide and the activated carbon based asymmetric device. So here we can see it. We see for the activated carbon, it is shows the symmetrical behavior, very uniform current response. But in case of the manganese selenide, we can see here the sharp peak. That means the high current achieved. And here is the beauty of the asymmetric devices. If we assemble it, first of all, it is increase the voltage window, and second thing is because of this metal positive electrode, it is shows a redox peaks or high current, so their performance or being achieved. But if we suppose if we will make the activated carbon electrode. So two AC electrode are sandwiched. So both AC electrode has the same type of curve. So their capacitance value or performance is not much improved. But if we see one is the EDLC, like electric double layer behavior, and one is the Faradic behavior, and we can use it, then we can get the higher performance related devices. And here we can see it, and because of two different electrodes they use, they generally get the higher voltage window, as from we can see it from 0 to suppose 1.5 volt. And also they get a very good energy density and the power density. We can see it here. Their power density is around highest power and the energy density they around the 1000 power density 1000 watt per kg, which is the other related work, that is they get the high performance. And also because they use the different electrode, and each different electrode has a different charge storage property. So they run a cycle, how much time it can sustain, and up to 8,000 cycles. We can see their capacitance value is almost 100%, as well as their Coulombic efficiency is also 100%. Coulombic efficiency is the another aspect or another things to analyze the electrode material. I didn't discuss about the Coulombic efficiency, but as roughly I can say it, Coulombic efficiency means we will check how much time it will take to charge and how much time it will take to discharge. Based on that that ratio, we calculate the Coulombic efficiency. For example, if any material that charged very slowly and discharged very fast, so that means their Coulombic efficiency is the lower, which is not desirable. Because if we make a device, suppose, and it takes charge so long time and discharge very quickly, that is not a useful, right? So that's why we check the Coulombic efficiency. And we can see it here. They light up LED two devices, and it can be sustained up to 5 minutes, maybe more than 5 minutes, but they shows it here up to 5 minutes. It can glow, so that means it can for completely discharge it is more than 5 minutes. Third one, another example for the asymmetric devices is the nickel cobalt phosphide. So here is the they make the nickel cobalt phosphide MOF. As I say previously, this is the special kind of structure called metal organic framework, which now it is research is going on through this type of structure, MOF structure, and it has some another property. I will not go details on that, but as I can say it here, they use the nickel cobalt phosphide based MOF structure, and in the 3 electrode cells, different nickel phosphide or cobalt phosphide and nickel cobalt phosphide to check the morphology and all these things. And they measure its 3 electrode cell system. First of all, to make any devices, it is important for the individual electrode performance. So for this individual electrode performance, as before I say, we use a 3 electrode cell system where we use a working electrode, counter electrode, and the reference electrode. So based on this setup, first we check the individual electrode performance. And once we get the individual electrode performance, and then we go through the device performance, device fabrication. So here, different material, different morphological changes of nickel cobalt they measure, and they achieve the specific capacitance. See, here is called the graviometric capacitance. That means farad per gram, or you can say it as a mass specific capacitance. That means how much material we deposited on mass related specific capacitance. And we can see it here. They achieve the specific capacitance value around 1,500 farad per gram. So based on this 1,500 farad per gram specific capacitance value and this material, and they use the activated carbon, and then they follow the charge balance formula. And the charge, after that, the charge balance formula, how much activated carbon they have to deposit, and they deposit, and then they assembled it, and after assembled it, they achieved a very higher energy density and the power density compared to the any other work. And also their capacity retention is also very good after 10,000 cycle. Maybe we can say it almost higher than 90%. And also the Coulombic efficiency, as we can see it here, Coulombic efficiency also 100%, which is very good for the supercapacitor, asymmetric supercapacitor devices. Next is the planar devices. As I told before that devices is the main type of number of devices: symmetrical, asymmetrical, planar devices. Actually, generally for the planar devices, symmetrical planar devices can be done, or asymmetrical planar devices can be also done. But mostly nowadays, only symmetrical planar devices are fabricated, because there are in planar devices there are some limitations, as I can say told you. So first of all, planar, what is the planar devices? See, if we see it here, planar devices means in one single electrode we make a one plane material deposit, and after different techniques, whether it is pattern or any other method, we can make the gap, we can make a structural pattern, and in between them we use the electrolyte and make a devices, or so this is called the planar devices. So for example, suppose graphene, we can see it here. This is called the planar devices. We can see 3 electrodes are deposited, and in between them there is small gap. So in that case, here we can use a electrolyte, and we can check its performance. So, and one example is for the graphene oxide based or reduced planar devices. So graphene oxide ink they make, and during the pattern or printing, so some method, screen printing method, they make a this type of planar pattern, and they do the electrochemical performance, electrochemical reduction, because to make graphene oxide to a reduced graphene oxide, and then they apply a electrolyte to make the planar devices. So generally, if anyone wants to make the symmetrical devices, they can planar devices. So symmetrical devices is the good option. Asymmetric devices is not a good option. I mean, it's difficult because as we can see it here, for planar devices, both the electrodes are the same material. So as I say, no charge balance is needed. But in case of the asymmetric, charge balance is must important. So then it's difficult to make the asymmetric planar devices. So generally, people are doing the planar devices symmetrical form. Here is the one example of the planar devices. And as we can see it here, they use the graphene and the polyaniline heterostructure base. Generally, planar devices, it is in structure very less, so that's why it is called the micro supercapacitor, because we can make a very small supercapacitor devices. So how they make the planar devices of the graphene and the polyaniline base? They use the graphite foil or the graphene, and they used for the graphite foil, they after formed to the and the graphene, and they use the polyaniline and make a composite, and then make a ink, or we can say graphene oxide and the polyaniline ink, and they in a silicon substrate. First they deposit a collector and a current collector, and then ink. After that, they ink, they make a thin film of the polyaniline and the graphene base, and after that they make a pattern to make the symmetrical planar devices, and then they use the PVA KOA. So one thing is, for planar devices, it is must important. We cannot use any aqueous electrolyte, because in plane we cannot put aqueous electrolyte. Otherwise, all the aqueous electrolytes goes around. So for that case, we have to use the gel electrolyte, and we can see it here. This is their planar devices, and which can achieve the capacitance value is around 180 millifarad per centimeter square. So because this is the area, they calculate how much area of the each electrode. So based on that, they calculate the areal capacitance, which is very good. And for the planar devices, it is one beauty is, for the planar devices, we can make any kind of connection, whether it is we can add the number of capacitance devices in series or parallel and all, so that whether if we want to improve the voltage window, or else we want a higher current, voltage window is limited but the high current, so based on that we can connect it through series or the parallel, and based on that we can see it here. Suppose device 1, 2, 3, 4. Suppose in case of the single devices, it is very poor. If number 4 connection, or suppose in number 2, see a parallel connection, series connection, we can see the higher potential window is limited by the high current. So long time it is charged. So based on that, we can whatever we need, we can make the devices. And also, since the planar, so this is the bending test, and also during the different bending test, they perform the cycle. So one is flat bend, flat blend, and they can claim their devices is during this condition, it can be up to 90% after 2500 cycles. For wearable devices, planar devices is the good option, because here we can make the pattern. So here are some example. For example, here this is the pattern they designed first, and they use this pattern and screen printing any material and screen printing method. They get the film deposited supercapacitor material deposited onto it, and then they next they deposit the current collector and or the other material first. Suppose in case here, first in pattern they first deposit the current collector, and then they deposit the metal oxide, and then they put the electrolyte. So, and this device is can work. And also this type of things in future application, if we suppose in planar devices, if we use a sensor and connect it through this device, it can these devices can be also used for the UV sensor. And there is also the devices how to make the pattern. One kind of pattern is like this. One kind of pattern, first they deposit electrode first, and after that in between them they deposit the graphene, and then they deposit the graphene and the ZNO nanoparticles, and they pattern it. So many type of structure or many kind of pattern can be done in planar devices. And for wearable device application, planar devices is the best thing, because it's flexibility and all these things is very good. And also it is the power consumption or the power requirement also very less for the wearable devices. So planar devices is the good. Another is the sandwich type capacitor. Till now we will see the two electrodes are patterned onto the one substrate, and after that we use the gel electrolyte, it becomes a planar. And but the sandwich is just opposite, where we deposit the different current collector, different substrate, and material deposited on the substrate, and then we make a sandwich. And in between them, as we can see it here, it becomes the sandwich like structure, where suppose we use a graphene. Suppose in case of graphene or reduced graphene oxide, we deposited one current collector, and other things we deposited on another current collector, and in between them we apply a gel electrolyte, and we can make a sandwich, just like a sandwich structure, and we can package it. So this is also the one type of device architecture we can make. As one example is here, a sandwich type structure, where both two electrodes, because in sandwich it is, we can make the any asymmetric devices, because we use the different current collectors. So different electrode materials, sorry. Suppose cobalt oxide or nanoporous carbon, different two electrode material are sandwiched together, and inside we put the electrolyte, and that can achieve the higher specific capacitance also, and also higher energy and the power density, because it is shows the high voltage window. Next one is the coin cell. As I think everyone see the coin cell batteries and all. So this is the one type of coin cell. This is also sandwich structure, and this is the coin making the coin cell. So here I will say how to make the coin cell structure. As we can see it here, this is the coin cell components. Where we have the positive and the negative electrode joints or terminals, and these two calls the spacer, and this is called the O-ring. And this is the after coin cell for testing we use it. And how to make then the coin cell. So first of all, we make any, suppose any flexible or non-flexible, that is okay, because in coin cell that is not important. So we can make a thin film deposited onto the current collector, and then we need to cut it so that it will fix it here. So for that case, we need a cutter. So what we will do, we will put the our deposited thin film over here and press it. So once this is press it will cut according to this diameter. So after this getting the electrode diameters electrode, now we will do the assemble. And how to assemble before assembled, okay, before assembled, first thing is, because we need a calculation how much specific capacitance. So if we calculate the mass specific capacitance, we need to check the how much material deposited, suppose in case of positive electrode or the negative electrode separately. And okay, now since consider all the mass, charge, all these things are balanced, and we make the thin film and cut it through for this diameter ring. Now, however, first we will use the spacer. This spacer is used to prevent the contact between this current collectors and the electrolyte. Why I am telling these things is a current collector, because inside, suppose we use the nickel foam, we cannot be connected through it here, right? So once the cell is prepared, this is the complete cell, we need to connect it here. So here we can say this is the, these two are the current collector. So this spacer, first we put here spacer, and then our deposited film, and then we use the gel electrolyte or separator or anything. In case of the if we want to make the aqueous electrolyte, use the aqueous electrolyte, then Coaxial is the good option, because here the evaporation of the electrolyte is very less. So after that, put one electrode, and then we use the separator and aqueous or the gel electrolyte, anything we can put. And then again we put the another electrode, suppose negative electrode, and then we put the spacer again, and then we put the O-ring, and finally we place it here and make the cell. And the uses of the, I already says the uses why we use the spacer. Now the uses of the O-ring is to make the connection is good, because it will press all the electrode, electrolyte, separators and all very very good manner. So that's why we use the O-ring. Sorry. We use the O-ring. So once all these things are assembled, we need to press it over here. So this is the instrument. We put our Coaxial over here, and we just rotate it. So once the pressure it's done, so it's just drop and make a complete compact cell, and we can measure its we can make a Coaxial related devices. So any batteries material or any supercapacitor Coaxial can be done during this method. So now applications. In what dimension we can apply our supercapacitor? As we can see nowadays, energy, all things in all applications we need a energy. So whether in our daily life, whether it is like our mobile phones or batteries, mobile phones or electric vehicles or laptops, we need the energy storage. So batteries and the supercapacitors are used. So generally for the application in supercapacitor can be used many things in automotive, like electric vehicle, in agriculture, in industrial, in medical, in consumer and the retail and in military, all these cases supercapacitor devices are applicable. Not only these things, we can use these supercapacitor devices as in a pacemaker, because this is the compact type of structure, and the stability and the long cycle stability and safety is also very good. So in the pacemaker we can use the supercapacitor devices, and also we can use tissue generation, or else in case of wearable we can use the supercapacitor for e-clothing or smart watches, glasses, and all. And also we can use these devices for the drug delivery detections, or the sensors, and all many things we can use the supercapacitor devices. So among this, one example I can share it, and it is called the sweat chargeable on-screen supercapacitor for the practical variable energy application. So this is the how this type of supercapacitor or this type of devices can be used. See, during this high humidity and all these things, suppose if we make a device and if we wear it, and the sweat out from our body, if that is act, and then from this sweat we can make a supercapacitor that can also applicable. For example, if we see it here, how it works. See, this is our human body, and sweat means it is the salt, NaCl, right? So what happened? First, they use a zinc air batteries. So two devices they use. So first they use the zinc air batteries. So when the electrolyte and connect to the zinc air, so zinc is converted to the zinc 2 plus. So it's released to electrons. So what happened? These electrons can go through the supercapacitor devices. So, and then it can work. So this is the device architecture, how they make these devices, and we can see it their performance. And the main application is, suppose we use it in a wearable watch, and then during physical exercise, when the sweat out, we can see it here. These watches are charged. So that is the one example for the wearable applications. And second one is the detectors, photo detectors. So how this supercapacitor is used? Suppose they make a specific special kind of structure of copper oxide and the nickel copper oxide, and since this supercapacitor, we can see it here. When the if they use the light on, so it is charged. If in case of light off, we can see it here, it is discharge is it discharge very fast. If we see it here, the capacitance, if in light on condition, it capacitance is increased compared to the light off condition. So this type of photo detectors application, this supercapacitor can be used. And we can see during the cycle of different cycle test, or light on and the light off different conditions, their charge discharge and we get the cycling stability. And we can see it here for the light on condition, its capacitance value is very increased. when compared to the light off condition. Only thing is, we can see it here, the stability for the light off condition is very stable, almost 100%, but it is very fast decrease. Although this is in the research in the research process progress. One thing I can say, the possibilities of these things is when you use the light on and the light off, so inside these materials oxidations and the reductions happen, and due to this oxidation and the reduction continuously happen, so it may the in stable form, and at for this reason its cycling stability is degraded, as we can see it here. Why these things happen? So this is quite a bit complicated to analyze, but as I can say only it in supercapacitor, if we make a special kind of material and also special structure, we can use it in a photodetector. And this is the one more example where it can generate the energy when the devices or the electric vehicle is braking. This is the prototype, and how they make the devices. It is first is here. They make siloxane graphene heterostructure based devices, and this is their electrochemical chemical performance. As we many times I already say how material process, I will not go through here, but main things I will explain it here. So they make a asymmetric they make a asymmetric devices. Sorry. Yeah, okay. They make a devices, and not asymmetric, solid state symmetrical solid state capacitor, and they get a performance, and which is very very good. Like specific capacitance value is 45 farad per gram, and different cycle test. After 10,000 cycle, their capacity retention is around 100%. But what is the application? They used first they used in the electric vehicle, not electric vehicle. They make a prototype where suppose this is the vehicle's wheel, and it's connected. First it is connected to the transmission, then motor generator, and then controller, and then supercapacitor. And what this is their structure, and what they are doing, they rotate the rotate these vehicles. So once this is start moving, once it starts start moving, suppose, and suddenly it makes a break. So during this controller, transmission, and the motor generator, the supercapacitor starts charge, and as a result we can see it here. Suppose we can see in driving mode, it is supercapacitor devices is the normal source, but when sudden it's start braking, so it suddenly increase, and then it's decreased, and then again driving start. So that means, suppose in the elect and they applied it like this way, and they LED bulb up the LED, and as they since this type of supercapacitor can be applicable for the electric vehicle also, not only charged when the during braking condition, supercapacitor can be charged, and it can used in the another way. And this is their devices, how much sustain they can say. Their devices can recharge the clock up to 24 minutes, and their devices can have a good energy and the power density compared to the other related works. And till now, and this is the one more example how supercapacitor devices are used in the for the textile application. So first one is the how they use. Suppose this is the normal textile clothes, and in that textile clothes, suppose silk fabric, they deposit the current collectors and then their materials, and make the electrolyte like this electrolytes, and make the devices, and that can light up the LED. Also good electrochemical performance, and also this type of supercapacitor can be used in clothes. And another more example for carbon nanotube based supercapacitor. And what they do is, first they make a separate cloth fabric yarns, and they deposit the carbon materials, carbon nanotubes, and they separately the gel electrolytes, and in between this gel electrolyte they make the pattern. This type of pattern can be seen the wearable the clothes, and we can use it, as we can see it here. We can use it into the clothes, and that can we can see it here how many devices can be fabricated. So overall performance, so to improve this performance, and it is also shows their energy and the power density is very high. So another is the textile based supercapacitor for the wearable. So they use a fabric, and they used fabric, and in experimental they in fabric substrate they deposit manganese oxide and the nickel cobalt oxide form, and like this they can get it. How they can get it? They first they make the different solution, and using the normal printer, using this liquid, they print it. Print it in this fabric, and which is much more flexible, and we can see it here, and then they assembled it and make it devices, and we can see it. They get the very good real capacitance, and we can see it here for the flexibility and the wearable application. We can make this type of devices also. And here is some real type of application, as it is done in our lab. I just want to show you. We make the asymmetric devices and light up the LED. We just this is our devices, and we connected it, and this is a collaboration work of our professors and IIT Roorkee, and this is the joint collaboration work, and we just we can see it here, our devices, and we connected through the number of LEDs, and after charge we just connected it and check it how much time it is fully discharged. So as long as it takes time, that means our devices is in good condition. So as you can see, when the time goes on, first the lights brightness start dimming, and we can see up to three minutes or something. It is completely disturbed. Another example is we turn on electric fan, and here we connect it our devices, and connect the turn on fan, and we can see it. It starts rotating, and we just checking how much it is done, how much time it takes. So now as it's completed, so is any questions? Hello, is any?
Yeah, it's already open. Session is already open. You can open your mic and you can ask the question. I also share the test question. You can see the test question in the chat box also.
Okay.
Please ask the question to speaker.
Good morning, sir.
Good morning.
So I'm Anand Raj. So regarding the current collectors, sir, what are the suitable materials you can just use for current collectors, and which can be demonstrated in a small room without any research facilities? Sir?
Oh, for any type of current collectors, you can use normal copper foil. Copper foil you can use as a current collector, or any nickel foil you can use as a current collector.
Copper is enough, sir?
Yeah, copper is enough. But now when using the copper, make sure when you make the assemble or make the devices, make sure it is not contact with electrolytes. Okay. Because if it is contact with the electrolytes, copper may be oxidized, so automatically reaction happened.
Okay.
So copper, so suppose if you in copper tape, or if you deposit any material, and just make sure when you make the devices, your copper substrate should be bigger, little bit of bigger, so that some after depositing some material, you have to cover some copper part by any insulating layer, so that it cannot be contact with electrolytes. This is only just for safety. Otherwise, I mean, copper starts reacting.
Okay. Thank you, sir.
Yeah, welcome.
Any other questions? Okay, can you, Bhaskar, can you answer your past questions, sets answer? Means, whatever you have discussed, given.
Okay.
Sir, one question, sir.
Yeah.
Sir, if green synthesized nanoparticles can be used for the film making,
yes.
for any of the cells?
Yes.
Thank you, sir.
Suppose if you want to make, you are talking about the green synthesis means biomass, right?
Yes, sir. From plant cells, we are synthesizing nanoparticles. Copper is a type of nanoparticles.
Yeah. Actually, nowadays, because of environment safety and reduce the cost effectiveness and all, biomass related materials also be used.
Okay, sir.
in
Thank you.
supercapacitor applications.
Okay.
Yeah. So now, Dr. Pandey, yours says
Whatever you have given the questions, you can open your form. There already answer is there, I know. You can just tell if possible, or otherwise I can discuss later, or I can send them later.
okay. Wait, I will try to open. No, that form doesn't open in my system. I don't know.
Okay, leave it, I will send them. I
Okay.
think it's already running net here. So I think there are no more questions to Dr. Bhaskar Pattanayak. So with this, I like to thank Dr. Pattanayak for his valuable time. I know he is very much busy for this work. I also work there in the same lab, and we have some papers, a lot of papers also. And this is the only weekend they can do their personal things, personal shopping, etc. And I also like to thank all the participants present at this moment and for their time. I'm very much sorry we are not able to give because I know the 15 minutes or maybe some days we are not able to give any time break. So some of you are suggested that we need a little bit bigger break. So we will consider this in the next page definitely. So with this, I like to thank Speaker Pattanayak once again. And we have that. But with this, I'm closing this session. Thank you, Dr. Pattanayak, and thank you all of us. So we will read.
Thank you to everyone. And, I hope you learned something from my talk. And if it is motivate you to work on the supercapacitor application, you are most welcome. Because this is a very good research topic and very good future prospects also. So you guys are most welcome. Yeah, thank you.